unless you tell me otherwise.
No, it's all good. It's nothing, nothing secret here.
Perfect. Okay, perfect. Let's start. So thank you very much for being here. Today we have a visitor, Jeff Hodgson, that I know from a long time ago. When I was a postdoc in Bonn, he was doing the PhD there. And he's from Perth, if I'm right, in Australia. And after Bonn, he went to Sejong, and now he's permanent there. So, perfect career.
Or perfect career.
Today he's going to talk about the Quasar distance elevator. So all yours. Thank you very much.
Yeah, thank you very much. It's nice to finally make it here. As anyone who knows me, I like Spain a lot, so it's a pleasure. And so today I can, and of course, everyone knows David. He was a career with me for a year or so. Yeah, and so today I'm going to talk a bit about the sort of stuff that I'm up to. My primary my projects, and we're now sort of expanded into like a whole sprawling thing of getting distances to quasars. And it's something that I shamelessly stole from an Indian postdoc called the Quasar Distance Elevator, as sort of making fun of the distance ladder, which hopefully everyone here is familiar with. Okay, so actually sometimes when I give this sort of presentation, I give a kind of more outreachy version, which is because actually I find that astronomers like it just as much as normies. And but I'm going to just do the very short version today. But actually, the whole story of the distance ladder and all these sorts of things, something goes back thousands of years. It actually goes all the way back to the ancient Greeks. So they knew the size of the Earth actually, even to a precision of about 15%, even like 2,500 years ago. They didn't even know pi back then. And then, so it turns out if you know the size or the radius of the Earth, you can work out the distance to the Moon. And then if you know the distance to the Moon, you can work out the distance to the Sun. And so I won't go into all the gory details of this sort of thing, but actually getting that wrong sort of indirectly led to the Earth-centered model of the solar system. It's a little bit complicated. But basically it all boils down to our good friend parallax, right? So the ancient Greeks, they knew about parallax. So I assume everyone here is familiar with parallax? Like, yeah, parallax. And yeah, so basically the ancient Greeks, they knew about parallax, and they're like, well, okay, if the fact that we don't see parallax means that these stars are either impossibly far away or something, they're not really there, or something else. And so they went with the something else option, and it took until Copernicus, at least within Europe, to correct that. Anyway, and so eventually in the 1700s or so, Kepler got distances to Mars and Venus, and ultimately to the Sun. Very clever the way he did it. And once we had that, we had improving telescopes by these days, and ultimately this led to measuring distances. And if you're measuring distances, that kind of turns science of astronomy into astrophysics, right? Because if you know how far away something is, then you know how bright something actually is, as opposed to how bright it appears to be. And that, knowing this sort of information led to the Hertzsprung-Russell diagram, amongst other things, and then ultimately we measured the redshifts to the spiral nebulae, as they called them back in the day. There was a big debate, famously, about whether or not these spiral nebulae were part of the Milky Way or not. And ultimately, Hubble came along and Lemaitre and showed that the further away a galaxy was, the more redshifted the galaxy would be, which is, and our current best interpretation of this is the is the expansion of the universe, and thus the Big Bang and all these sorts of things, or the cosmic egg, as Lemaitre put it, which I think is actually a much nicer expression. And then much more recently, in the 90s, they worked out that they could standardize type 1a supernova as a this kind of standardizable explosion of sorts. And that led, basically, we found that the supernovas at high redshift were fainter than we expected. And this is the so-called accelerated expansion of the universe, or dark energy. I don't personally like the expression dark energy because I think it kind of overinterprets what it is. We really don't have any idea. But anyway, that's, and they got the Nobel Prize back in 2011 for that. So that's the very, very abridged history of it all. But the story does go back a long way. And so we get to today. And so famously, we have the Hubble Tension. So this has been sitting around there for good 10 or 15 years now, I think. And so basically, you have these early universe probes like the cosmic microwave background, and we get a consistently sort of low value of the expansion rate of the universe. And if you use late universe probes, like using Cepheid variables and that sort of stuff, we get something like 73 kilometers per second per megaparsec, which is really strange, actually, when you think about it. But anyway, and so this tension seems to be kind of persistent. But still, people are sort of arguing about it. It's like, well, okay, is there calibration issues in the data, or is it really new physics or something like this? And then, sort of quite famously, we've got the Dark Energy Spectroscopic Instrument, DESI. They have latest results, and they're claiming there's a hint of what time variable dark energy is, sort of the way that people put it. But the thing about it is still, you need to combine it with different probes. So what they're actually measuring is something called Baroynic Acoustic Oscillation. And the BAO signal is a relative distance, actually. And you still need to calibrate it on the distance ladder or some other way. So it's definitely interesting. What exactly it all means, I think, is still a bit unclear, which is, I think, what makes it so interesting. And so with this sort of background, what we really want is what we'd call a single-rung distance indicator. Something that means that we can go directly to the distance as a function of redshift without having to calibrate on lower rungs like parallax or Cepheid variables, these sorts of things. Indeed, and so this is kind of the big problem with the supernovas and the BAOs. So the current distance measurements are anchored in the local distance ladder. And so what, unfortunately, is sort of unavoidable, like if there's any unknown systematics or anything like this in the lower rungs of the ladder, then it's going to give you propagating errors down the line. Now, of course, the people doing these things are very, very careful. Not to say that it's wrong or anything like that, but it's just an unavoidable problem with doing this kind of thing. And similarly, though, on the side of the CMB measurements, anyone who's met someone who does CMB stuff know that the way they do the foreground subtractions and stuff like this could be dirty too. Once again, probably fine, but there's definitely potential there for just some observational systematics topic, something like that. So ideally, we want something to come along that's completely outside of their logic and do the same sort of thing. And that is basically where I went. So I was like, okay, so quasars, right? AGN, so basically, what we're trying to do is we're trying to use them as a standard ruler that is bypassing the local distance ladder entirely. I'm not the first person to think about that, of course, and I'll talk a bit about some of the other people who have tried to do this over the years. Microquasars, I'll talk a bit about that too, because microquasars have parallax, or sometimes have parallax distances. But fundamentally, the problem with AGN, and historically this has always been the problem, is that it's quite difficult to disentangle if they're highly variable and far away or relatively faint and nearby. And so the solution that I proposed was actually just, well, it wasn't really like, it's kind of an old idea, but resurrected it, was to use this variability to our advantage. But before I get to that, so talk a little bit about some of the historical attempts to use quasars as distance indicators. So over here we go, we've got M87 over here, so I'm sure everyone is familiar with this particular picture. Anyone not seen it? Yeah, like, as I like to say, I think scientifically it was not that exciting actually, but it is cool. I'll definitely give it that. And everybody knows what it is. Okay. So the AGN, the most continuously bright objects in the universe, long desired as a standard candle or ruler. Reverberation mapping, and actually related sort of thing, this megamasers, I'll talk about that in a second, is quite good, but you need a black hole mass. These Leonid Gurevitz and some of the guys started these size scales back in the 90s. Doesn't really work. People even looked at it quite recently. And other people looked at like these parsec or larger scale structures and these sorts of things to try and do the calibrations. Yeah, it kind of sort of works, but not also well. So basically, we need better methods. So probably the most famous sort of recent methods or a recent attempt is by Risaliti, and it's actually there's an Italian group here where they basically calibrated this relationship between the X-ray luminosities and the UV luminosities to find sort of Hubble diagram over here. And they claimed a deviation in high redshift from the expected cosmology. And there's another paper out in 2022 which says that, which is basically here, which says that in fact the results still stand up. I'm not expert enough in these things to tell you if this is correct or not. But probably the most important point from our perspective is that it still actually needs to be calibrated using the type 1s. So still, even this method still sort of has the same sort of potential problems that if there's something wrong with the type 1As and Cepheids and these sorts of things, it's going to propagate into these results as well. So, so it's definitely interesting, but still there. So the Scorvid's count methods are actually people have been looking at this for a few years ago, and actually a group in China sort of took the idea and continued it, and actually some promise I think there. I've read their papers and I'm like, that's actually quite potentially possible. I won't go into the details of how they're doing it, but they claiming seem to be they can measure the flatness of the universe and a few other things. So it is quite promising, but equally they haven't had a paper out for like 5 or 6 years now. So I'm not sure what the current status of that is. Unfortunate. Probably the most robust method to getting AGN distance is the megamasers, and there's a big project on the VLBI over in the US called the Megamaser Cosmology Project, where they mapped maser disk in 20 galaxies and measure sort of gold standard black hole masses and these sorts of things. You can see this is very nice bit of data here. Once again, I won't go into all the details. It's basically a purely geometric method, which is quite nice. And what the Hubble constant they get is the high value, 74, so something like this. But it's only from 5 sources, so potentially there could be like issues with peculiar motions, these sorts of things. But nevertheless, it's very cool. The problem with it is that it's observationally very expensive. Okay, that's not itself not a problem. The bigger problem is that we can only do it at a very low redshift. And it's just very rare and very hard to find. So I think they've got 20 in total, but really, even out of that 20, there's only 5. And there's a whole bunch of other issues there. But it is pretty cool. So I do like it. And one day, hopefully, we'll get somewhere. Okay. And that's, now I can sort of lead into what I'm up to. And so we call it the standard speed gun. And I've got 2 slides here, so I'll just say the same thing, basically. But basically, the idea is that, actually, I might even skip. I'll skip ahead onto this slide. So basically what we're doing is we you can kind of say, all right, if you have a flare go off inside an AGN, in effect, you time how long it takes for the light to cross the source, times that by the speed of light, and that gives you size in meters. Then you measure the apparent size using VLBI, and the ratio gives you the distance. That's it. It's actually incredibly simple. As you might expect, there's a whole bunch of issues in trying to do something like this, but probably critically from the perspective of a cosmologist is that all our systematics and issues are completely different to theirs. Right, so we obviously do have lots of issues, but yeah, they're different issues, and so that could be very, very powerful. Now, one of the things is that in addition to being able to do the distance itself, it's in principle at least a single rung distance indicator, and we can go from like basically redshift 0. Have to even inside the galaxy, all the way out to like redshift 5, 6, 7, 8, or something, using the same method. So if we can really pull this off, for reasons I'll explain later, then this is very, very cool. And by the way, we kind of have done it, but I'll talk about that. So, okay. So we've been trying to look at this with the archival data. So arguably, what we're doing is better than using the supernovas. Because we can measure the Hubble constant and the omega and the matter content of the universe under a random CDM model at the same time. Right, so at the start of saying, well, you know, we get all these interesting hints of time variable dark energy and these sorts of things, but ultimately you're combining different probes. So you're combining low redshift stuff, high redshift stuff. We're using the same method in one go. And so to concretely show you what I'm talking about, back in 2020, quite a few years ago now, we published a case study in 3C84. Actually, we have this thing about the geometry done here. Annoyingly, this becomes important later, but I'll come back to it later in the talk. But okay. But before I get there, I've been told that not everyone here knows much about VLBI. So, although I think Lorena came and gave a talk recently, but nevertheless. So VLBI. So basically, there's two kinds of ways of doing VLBI. There's an astronomical VLBI. In effect, what you're trying to do is you assume that you know where your stations are, and then you're trying to work out where on the sky your radio light is coming from. That's the very basic idea. And so the further apart that you move your dishes, the more precisely on the sky you can measure where your radio light is coming from. Now, there's another form of VLBI called geodetic VLBI, where they fit the logic. What they say is, like, okay, the background quasars are in fact stationary, and then we try to measure where the stations are. And so if you see on the news, for example, like there's a tectonic plate or something that's moved by like a few meters, yeah, this is how they do it. Right, they're kind of cool. Like where earthquake, tectonic plates moved, and it's due to referencing everything against the background quasars, which I think is pretty cool. So you can sort of think of it as making an image via making lots of 1D slices. That logic is ignoring phases. In effect, we're measuring the Fourier transform of the sky brightness. Cool. So the cool thing is that it means that we can do really incredibly high angular resolution. So we can get up to about 50 micro arc seconds, or even better with the EHT, like up to 20 micro arc seconds or something like this. Which means that I can make a completely terrible joke and say that. So basically, that kind of angular resolution is a bit like if you put your phone on the moon, we can resolve that, right? That's how small we can see, which means I can make a joke about putting a galaxy on the moon. I'm sorry. I'm not really sorry. Anyway, so anyway, all this talk about geodesy does actually become important later. And yeah, there's a relevant XKCD, if you're not sure if anyone's seen it. Interferometry is so cool. If you put two small dogs a large distance apart, they can function as a single giant dog. I'm not sure if that's how There you go. Okay, too much fun for now. Let's get into boring things. Okay, so with that out of the way, so back in 2020 we published this. It's also 384. If anyone familiar with 384? Right. Okay, so it's one of these famous radio sources. So M87 is sort of the other famous one, but 384 is kind of there doing everything completely different and weird just to annoy everyone. It actually has a supernova type 1A in it, which is kind of nice. Except that it turns out that it's weird subluminous type 1A, so we couldn't really use it as a story for later. But okay. We could measure a distance of this using this, standard speed gun approach. All right, so here we go. So this is a VLBI image. So if, for people who are not familiar with VLBI, like the angular resolution here is crazy, right? So this is obviously the exact angular scale depends on the distance, but roughly speaking, this is going to be around 1 parsec, right? So it's 2 or 3 light years across, something like this. This is and this is like 80 megaparsecs away. So it's like a really tiny thing. The black hole's probably down here, and you've got the jet sort of being burped out, for want of a better expression. Okay, but for our purposes, actually, we're looking at this sort of thing down here. And then, over the course of a few months, it gets brighter and brighter and brighter, and brighter, like this. And then it fades away. Right? That's basically it, right? So, yeah. Very, very cool. Great. And then, what that means is that that's basically what we do. We just say, okay, we calculate this e-folding timescale. This thing grows exponentially, and it gives us takes 146 days of e-folding timescale, and it gives us a distance of 72 megaparsecs, which turns out to be about 73 for short. Yay! Okay, only thing is you shouldn't believe it. Like, it's cool proof of concept, but it's one source, all sorts of things. Don't take it too seriously. We had to assume that the Doppler factor is only 1. We had these geometric assumptions, a whole bunch of things, but I'll come back to that later. Actually, by the way, in this particular source, 384, we think that the peculiar motions, so if you're not familiar, peculiar motions are the sort of random motions that the other galaxies near to us have that is not an reflexive redshift, that's not cosmological origin. But we think it's not very significant for various reasons in this source. But anyway, which puts us basically there. We're not so competitive, it's not at this stage. But hopefully we can do better. Okay. Now, I'm not going to go into too much detail here, but all I'll say is that, so in the case of 384, it's a low redshift source, and we could basically ignore the Doppler factor. Now, if you know anything about AGNs, especially if you're doing VLBI, you'll know that you get all sorts of weird relativistic effects. So you have like apparent superluminal motions, and things are very variable and bright all over the place. So you need to at least try to correct for this for high redshift sources. And you have to be careful because there's going to be an obvious inherent bias here because, especially as you go to larger distances, you're going to see more Doppler boosted sources because you can see it, right? So and that's okay so long as there's no bias in your actual correction for the Doppler factor itself. So you have to be quite careful about this. And then, once again, I'm not supposed to put equations on the board. The short version is, basically, we think that there's some kind of maximum energy density, if you like, that these sorts call it intrinsic brightness temperature. But it's basically an energy density. And we say that in quasars or blazars, there's a maximum true energy density these things can get to. It's called the equipetition limit or something like this. Doesn't really matter what the value actually turns out to be, so long as it actually is a limit. And that is actually what we're using to make these relativistic corrections. And actually, it's pretty good. But the only thing is that you have to assume that there's no evolution in this particular energy density value. So as long as it doesn't evolve with redshift, this is a surprisingly robust way to do things. But the other problem is that because we can put any old value in, means that it's a relative distance. So it doesn't give us a single rung indicator. It's kind of similar to the type 1As or the BAOs, because you still have to have a some way to calibrate this TVX value, this energy density. But nevertheless, you can still do it. So we went ahead and did it. So I started this project, and because I'm an astronomer, I have to come up with ridiculous forced acronyms. And so what I came up with is Quackers. I'm from Perth in Australia, so if you know anything about Perth, you might know that Quacker comes from Perth. And so for Quasar observations on the KVN from Korea to Australia and South Africa, and occasionally Spain, depending on my mood. And so actually in practice we do both. So I call it the Quack array. And so it's a bit up there. The observations are changing a bit, but basically we're observing on this huge big triangle here. So between Korea, the KVN, Opera telescope down in New South Wales in Australia, and Hardweg or Hardrail over here in South Africa. And for a while there, we were actually doing weekly global VLBI observations so it was actually a super ambitious observing schedule, and we're doing it. It's basically me and a few students basically doing this. It's pretty cool. Now the other cool thing about it is we have this thing called Astro2Geo. So this is where the geodetic VLBI stuff comes in. So if you know anything about VLBI, you may know that historically, astronomy VLBI and geodetic VLBI were like water and oil. They don't just talk to each other. They'll just go, oh, hello, spread out, right? Entropy. And then, but then, luckily enough, one of the geodesists in South Africa actually uses a nice person, and that was like astronomers. I was like, oh, cool. Actually, by the way, I went to South Africa, and that was awesome. Like, we went on a work trip to Safari, and anyway, but that was very nice. And so, anyway, the point being, by working with the geodesy people, we got telescope time that we could never have got by working by ourselves. Because at the end of the day, we are observing the same things. So we were observing quasars. And so by sharing, so basically what happens is they get a very nice, useful southern hemisphere baseline. And in return, they're monitoring my sources as part of their observations with the US Naval Observatory. So it's a bit of a win-win, basically. And so, which is really cool. We've got mountains of data. We're starting to work through it. Yeah, this has been ongoing for a few years. MOPRA broke down. I'm trying to fix it, but yeah, pretty cool. And yeah, we observe roughly every month with Yebis as well, which is over in Madrid. So basically, as things currently stand, we're doing monthly, like this, monthly on the Spain one, and then in between we get a monthly observations on the American VLBA network. So in practice, that gives us two weekly cadence. So every 2 weeks, we're monitoring these 50-odd sources. So yeah, that's pretty cool. But yeah, like lots of work, of course, but I'm kind of impressive that we pulled this thing off. One thing we'll say is that Thailand is joining, so which will be in here. This will really improve the UV coverage. But that's a detail for me to work out. Yeah, so you can see that this is what the data actually looks like. This is Vietnamese. This is like that's good data. This is our data. Is everybody here what we're looking at here? This is like UV coverage. Yeah. So the UV coverage, I like to think of it as like this is what you would see if you're at the source looking down at the array, and the more dots on here, the better image you can make. As you can see, we've got basically no dots. So indeed, so it's very limited, and what we found is actually quite difficult to actually extract size variability information, which is ultimately what we need from this. So we came up with a kind of clever way to do this. So what we did is we're like, okay, we'll actually compute the closure phases on the big triangle. And so I won't go into deep interferometry for you, but basically, if your closure phases are 0, it means that you don't have any unresolved substructures, very roughly speaking. And so because we're using the long baselines, well, probably it's not unresolved. So in general, and that seems to work quite well, actually. The only problem is that it's observationally expensive. So it's internally self-consistent the way we're sort of doing these things, but we go from like 20 years worth of data and you get like 10 detections out, because you need all of these things to work out perfectly. But we're working on this to make it a bit less expensive observationally. But nevertheless, we went ahead and did it. This is my student, Sejong. I won't bore you with all the details, but just with these very few sources here, we were actually able to extract out the omega M measurement. Not a very good one, but we're still not, I wouldn't, you're not going to win any prizes for this measurement, but nevertheless, even from just all this limited data and this just quick and dirty, we're able to do it, which is pretty cool. And it's just a relative distance, of course, so we can only get omega M, we can't measure H0 doing it this way. But what I can also say is that as we route and improve the number of data points here, basically the error bars go down. So in principle, we can just sort of, if we crank up the number of detections here by an order of magnitude or 2, then our error bars will go down by a factor of 10 or 15 or something like this. Ignoring any potential systematic errors and that sort of. But anyway, sorry for all the gory details. The main point is that, we're actually getting some early results out, which is cool. All right, but then what about this absolute scale? So we've been talking about the need for a single rung distance measure. So what I said before is a relative distance and still needs something to calibrate. And so are there ways that we can actually set the absolute scale and make a true single rung distance measure? And the answer is yes. And we have 2 primary ways that we're approaching it. One is that we fit a jet model onto the data. The other way is to use counterjets. Now, both of these have their problems, and also there's also microquasars, but I'll just quickly talk about that later. And then when I put all this together, I built the quasar distance elevator, which I think is a quite nice name. It's much better than your comment or some of the other terrible names astronomers come up with. Okay, so let's talk a little bit about the jet modeling. So I won't bore you all to sleep with all the details of how this, but basically it's called a Blanford conical jet, and it's basically synchrotron physics with a conical jet geometry at its very, very basic core. And you need a whole bunch of additional observables. So you need proper motions, you need core shift measurements, which is like the opacity measurement in effect. You need turnover quantities. Once again, you can ask me later if you want to know the details about this. Global K going to be perfect for this or not? Once again, these are details. But from your perspective, we went ahead and did it, and thanks to some heroic efforts of my student Europe. As I like to point, I'll put this in a talk like this, but I wouldn't put it to a paper. But I say it's dirty and it's noisy, but we managed to do it. This is it. We've got only from 5 sources out of the archival data. It turns out having simultaneous measurements is very important. But the bits that probably, if you know anything about cosmology that you'll care about, is that we can indeed pick up both H0 and omega M. Our Hubble constant measurement is more of a lower limit, I would say, at this point. But the really interesting thing is that we only pick up omega M with Hubble constants, which is also sort of connected with our systematics. So this G here is kind of about systematics in some sense. We only pick it up when H0 is above 75. So what that means is, like, if this is correct, big if, but I'm not going to sit here and say once we do get more data, we'll see. But if this is correct, is pointing towards the Hubble tension being real. Right, so this would, if it turns out that we're correct, it basically means that it's not just calibration errors. And it's actually pointing towards that the Hubble tension is indeed new physics, or something's going on. So that's pretty cool. So I'll move on. But of course, the obvious problem with doing that is that you're introducing a model dependency. Now, I would argue that, yes, that's true, but it's hard to think of ways that would systematically bias things. Nevertheless, it's possible. Better way is to use counterjets. So if you have a detected VLBI counterjet, then in principle you can make a purely geometric measurement, which is much, much better. So one of the problems with doing this is that detecting counterjets is rare because they're Doppler boosted, which means they're going to be Doppler deboosted on the other side. And yeah, nevertheless, there's two ways we can actually use these counterjets, and you have to make another assumption, of course, which is that the jet and the counterjets are identical. On one given source, this is probably not true, but on average, this should be true, you would expect. And anyway, just submitted a paper on this. This is a good friend 374 again. So if you have the counterjet and you have variability, you can combine everything and you get a geometric distance to the source. And now I sort of hand wave my way past this geometry assumptions sort of thing. And so if you do anything, so basically it's a bit complicated, but in effect, what's going on is that if the source is a sphere and you integrate over the volume, you get a slightly different answer depending if you're a disk or a sphere, right? It's a real subtle thing, and it gets into the details of interferometry and things like this. At the end of the day, the exact size measurement you make depends ever so slightly on which assumption you make. It's only a few percent thing here, so it's not a huge thing. But it turns out, annoyingly, that if you make the disk assumption, you get 68. If you make the sphere assumption, you get 76. So it's like, what is wrong with the universe? Why can't you just hear us and why do you have to be exactly like that? But that's what the universe is telling us at this stage. So from these observations alone, we cannot differentiate between the two. But it's still pretty cool that we can do it. I would say. So I'd say that it's a pretty good internally self-consistent way of doing these distances. And in principle, I've been thinking a bit about this. Maybe we can actually determine this directly from the data if we have good enough SNR. I have to think more about that. I really need to talk to someone even more expert than me on visibilities and these sorts of things. Anyway, but the other way to look at this is say, well, okay, what if it turns out that our jet modeling results are correct and the mega mazes are correct and all that sort of stuff? Actually, it points to the sources having a spherical geometry, which is kind of cool from an astrophysics perspective, but yeah. But we'll see. And then there's another way of doing this, which has been worked on by my student Daehyun. So if there are many sources that are detected, we can assume that there's a constant called gamma theta j, which is the Lorentz factor with the intrinsic opening of detail. Turns out people have looked at this with Mojave samples and stuff like this, and it does indeed seem to be a reasonable thing that you get a consistent value over all sources. If you can do this, then actually it's really nice because you only need three observables. You just need the proper motions, the apparent opening angle, and the jet counterjet ratio. So doing it that way, so we're just looking into this as like single rung, and yeah, it's pretty nice actually. The only problem is you actually need to measure the opening angle very well, and actually this is a whole can of worms. But if you can pull it off, it'd be amazing. But the reason I'm sort of thinking about these sorts of things is that as we move into the SKA, especially SK VLBI era, Because at the moment we have about 10 sources or something we could do these sorts of things on, which is not very great. But as we move into SK VLBI, we're going to be going to 10 to hundreds, maybe thousands of sources potentially. And then this sort of method becomes extremely powerful. And so, of course, not happening next year or something, but also in parallel, we're going to have like these wide fields VLBI imaging with SKA and these sorts of things coming along. So it might be that we can really do some very powerful things very easily, actually, like shockingly easily. We'll see. It's just one of the things that I'm thinking about now. And microquasars is so a student in his master's thesis looked at applying these methods to microquasars with parallax distances. I found some interesting things like the 1D variability timescale seems to match to the, if you have a 2D shape, it matches to the major axis, which is what you'd expect. But but nice to confirm. And as I stole this picture from a grant application I put in recently. Well, it's basically just saying the same things. All right. So that's cool. These geometric distances you can't just deal. The jet modeling distances can be done now. Early results are very tantalizing. But the big question is, are we actually correct? And in order to answer that, what we really need is a global KVN. Oops, what is the KVN? So the KVN is the Korean VLBI network. So it's really cool. It's a dedicated VLBI network now with 4 stations. Recently, 4th one opened in Pyeongchang, not Pyongyang. Pyongyang is North Korea. Pyeongchang is South Korea. This is where they have the Winter Olympics. Anyway, the cool thing is it operates at four frequencies simultaneously. So it means we can get these turnover things, core shift, a whole bunch of all these parameters. We can get it all truly simultaneously at the same time, which means that actually all these problems with like non-simultaneous observations and stuff are solved. So what we really need is to do these Quasar observations but multi-frequency and do it high cadence. And the cool thing is, I reckon if we actually get the time to do this, then if you gave me 48 hours of KVN time per week, I'll give you percentage level precision on cosmological parameters. Negotiating with the Koreans on that one. So we'll see. Because quite a lot of time, but it's precision, of course, not accuracy. So it could be details like this. If you just square root n with 500 sources results, we're getting down to percentage level single rung distances, which arguably is better than anyone else, which is cool. Great. But then I'm always ambitious. What if we could do even better? And okay, so parallax is the quote-unquote gold standard. So I started thinking about this recently. Could we do space VLBI to measure the so-called secular parallax? What is secular parallax? Well, in normal parallax, we use the Earth-Moon as a baseline, right? What if we use the solar system's motion around the Milky Way as your baseline? So it turns out the solar system moves around 50 AU per year, something like that. And so this baseline is always going to be ever increasing, always ever increasing like this. And so I've done some back of the envelope calculations, and short answer is yes, I think we could do it. It's just be merely expensive. So could we do it? Yeah, I think so. And so luckily enough, there is a plan led by Sasha Tripper over in Seoul National University for a project called Capella. So what that would be is a 690 gigahertz space only. So there would be no space to ground. And so maybe with 4+ low with all the satellites. The idea, actually, the original plan was basically you sit up there because you're in space, you have no atmosphere to worry about. So you can actually fill out your UV coverage over the course of a few days or something like this. So you basically have like the flawless, you see, this is the point spread function down here. You basically have a flawless UV coverage. That was the main aim for this. And then I was like, so, actually, I was thinking about doing like the VLBI, and somehow I got into this. And so this is a real plan that we're starting to think about. And with something like this, I think we could actually do it. But in the shorter term, we're thinking of something called MIMOSA, which is a 90 gigahertz or 3 millimeters of Pathfinder space VLBI mission, which would be only 2 satellites initially. But I did the back of the envelope maths on this, and I think even with something like this, we could measure the cosmological parallax to some of the nearby systems like M87 or Centaurus A, something like this. So I think it's actually very, very plausible. So actually, this calculation is for the edge of the universe, by the way. So in theory, it's very doable. So the parallax after about 3 years of baseline would be something in the order of like 20 to 30 micro arc seconds, which is for astrometric precision extremely doable. Of course, it's going to be astrophysical uncertainties, local proper motion, so it's probably not the redshift. What are you actually measuring if you're measuring to M87 or SNA? Okay. All these sorts of details we need to think about, but even to one of these sources, if we could actually pull it off, it'd be amazing, right? So it'd be pretty cool. So can it be done? We think yes. Just expensive, right? So if you want to throw a few $1 billion at it, hopefully they do. The thing is, I'm doing my homework on it now. I'm planning to write a paper and sort of demonstrating the plausibility of doing this to probably to SENA would be the obvious standard actually. So astrometric precision goes with SNR, as you can see here. So actually, one of the interesting things about this is that this plot here is over a 20-year baseline, but this is like somehow the worst case scenario. But this is like the minimum parallax that you would ever expect to measure in this sort of way. And we're talking about order 0.5 micro arc seconds, which it's difficult, but doable. We think, at least. We'll see. But if we pull it off, I like to say this would be like the measurement of the century, if we could actually do it. Like we would just destroy everything else. So we'll see. One of the other things, so one of these other details, so I think I've got it on the next slide, but well, I think it's on the next slide. Okay. What would we actually reference against? Right? So there's many things that, when you start thinking about this, there's many details you need to worry about. So one is actually the deflection of light rays of the solar system itself, like Jupiter and the sun, and have to take that into account. Okay, you can do that. That's difficult. But we probably also need to launch a calibrated satellite. So in normal astrometry or geodesy, what you're doing is you're referencing against the background quasars. But if you're using your background quasars as the thing you're measuring to, can't do that anymore. So I was like, okay, maybe what we do is we launch a calibrated satellite to the moon, or maybe to one of the Lagrange points, and then we measure effectively counting the phase, number of phases between here and there on the sky, and then do it again 5 years later. Actually, do it probably every year. Just do this, and as you go longer and longer baselines, you should see that for more distant sources, you would have less parallax compared to local sources. That's the rough idea. But there's loads of details you have to think about, like, so especially for MIMOSA, which is only 2 satellites, like actually the config, where you launch it to in orbit. So if you're orbiting this way, you can only sort of look that way. So if your source is this way and you're orbiting this way, not so good. Lots of things to do. Okay, here's a question for you that'll cook your noggin. What would we actually be measuring in this situation? Would we be measuring an angular diameter distance? A co-moving distance? Turns out the answer to that question is not trivial. And it's, yeah, let me down a rabbit hole answering that question. And the answer seems to be actually we measure something completely different. It's closer to a co-moving distance than angular diameter distance, but it's more like an actual just like parallax distance of sorts. Anyways, it's a much more subtle question than you'd think. Anyway, these are the things I'm thinking about these days because I actually reckon we could do it. It's kind of fun. Yeah, we'll see if something like this actually gets built. So there you go. That's my summary of the things I'm up to. So all the big questions basically boil down to distances. Our early results from our jet modeling, multi-frequency VLBI stuff is potentially pointing towards something interesting going on, not just calibration errors. Question is, are we actually correct? To answer that question, I need a scaled-up global multi-frequency Quasar project. Moving to the future, get around the jet modeling problem with using geometric distances on SK VLBI. And if I'm being really ambitious, let's get rid of that completely and let's just do cosmological secular parallax. You can have it for the cheap price of only a few $1 billion. So, okay. Let's see if we can pull it off. It better be amazing if we do. And yeah, thanks a lot.
Thank you very much. Very nice talk. Questions?
Thank you. Thank you for the talk. What was that again? With some data points with linear fit?
Here?
No. One before.
Here or?
I don't remember.
I think the only one thing with a linear fit like this one, or?
Oh, yes. What was it?
This is just the folding time scale. It's just flux versus time.
Can I see a turnover there?
This is just so basically all this is this, the flux of this component over time, and then it peaks in brightness and declines. And that's, yeah.
It is like one time even?
Yeah. So it's just literally, it's the flux of this component in graph form. Yeah.
Like it is not periodic.
In this particular case, no. Yeah.
Thank
So there's no, as far as we know, there's nothing periodic going on. Saying that, some people claim that, yeah. But in our case, we don't even need a periodicity. All we need to know is that the causality arguments hold up. That's the main thing.
The variability is stochastic.
Yeah, that's the assumption. Yeah.
Thank you.
Okay.
In this particular case, do you take into account the angle with respect to the line of vision?
As in a relativistic sense?
Yes.
So, no, is the short version. In this particular case, we knew in advance that it's not highly relativistic, so we just ignored it. So it's just, we sort of said like, it's only going to be a 5 or 10% effective at worst. So this is where the counterjet stuff comes in. So of course this is a little bit unsatisfying. So then we did go and do it with the counterjets to determine the viewing angles and the Lorentz factors and these sorts of things, the relativistic Doppler factor. And then it turns out, in this particular case, yeah, really is like very small effect.
So in the general case, you need the counterjet to get the gravitational.
Yes. Yeah. So that's the best way to do it, is if you can detect the counterjets, then and you have the variability, then we can basically solve the entire system. Only systematics becomes your geometric assumptions and also the C delta T assumption itself. So that's why indeed. So if we can do that, then yeah, it's actually super powerful. Just at the moment, it's just not many sources, unfortunately. Yeah.
Can you explain how do you measure omega m simultaneously? Because I don't remember much about it.
But basically, it's pretty basic. You just download the Python package for flat lambda CDM universe, and then you fit it onto your distances versus redshift.
Okay.
Yeah. Yeah, it's nothing too complicated there. It's just that as things currently stand, there's no other method that can do that. You have to combine it with other probes.
Hi, very nice talk. So, in one of your slides, it's mentioned that the variability can be used like in our favor because these sources has a lot of variations and in multi-bit wavelength you can see different things. So I didn't catch where we can use that in order to constrain the Hubble constants. Maybe in that way, or maybe I missed that. Oh, I don't know if well.
So basically there's a few things. So basically for the high redshift sources.
It's the Spanish hit.
Cool. So basically, for these high redshift sources where we do see strong relativistic effects and stuff, we use this intrinsic brightness temperature to kind of quick and dirty calibrate our these effects. But does that answer your question? Or?
Yeah, yes, yeah, well, I don't know because I am trying to, I don't know too much of Quasar, but I know that variability also is, if you want to see a flare in radio, probably it's not quite special with other flare, probably the variability there can affect, but I was thinking in that way, but probably it's not.
So if you have like overlapping flares or something like this, VLBI saves us in some sense because we have such high resolution, we
Yes.
actually resolve the actual thing doing the flaring. So I think people who don't do VLBI don't quite appreciate just how high resolution these things are. Like, yeah. Like some people, like if you come from the optical world, like no, just knock it up another order of magnitude. Yeah. So.
Is there so for this technique to be applicable, do you need the quasars to be for certain luminosity? Which are the requirements for the sources in order to be suitable for this?
Not really.
Just having a jet.
As a general rule, yeah. So basically,
the variable.
Yeah. So luckily, it's a little bit, almost a bit circular, but like basically the sources that tend to be bright enough to be seen like this tend to be hitting these sorts of limits. It's not a hard rule, but it seems to the first approximation to be correct.
And are the physics driving the variability always the same? Because I remember, for example, in M87, you have this particular region, HST1, which is persistent in space. So it's probably the acceleration region. And the variability there might not necessarily be the same as in the blobs that emerge or move on the.
Yeah, so physically speaking, probably what we're looking at, fingers crossed, is something like a recollimation shock. So it's something like HST1. Right, so probably what's actually physically what we're looking at is a relatively stationary recollimation shock. So you've got the jet being blasted out into space, and then at some point the internal pressure of the jet equalizes with the external pressure of the ISM, collapses in, you get a Mach disk, and then you have a sort of disturbance in the jet that goes down the jet, hits the it's this recollimation shock, and then you see gamma rays and all sorts of things going on. So that's kind of helps us because we think, well, if that's happening, probably our C delta T assumption is going to be pretty good because there's just so much energy getting blasted into the system. But on the other hand, we're going to get relativistic effects. So, but then we also can probably apply our maximum intrinsic brightness temperature assumption. So actually, if you to sort of lead a little bit further on, the bigger question is whether or not this value evolves with redshift, and turns out yes, unfortunately. But we can handle it. It just increases our error bars in some sense.
I had just a comment. So when you show us in the introduction the different ladders that we can see to measure H0, there is also another objects. There are star-forming galaxies that you can also measure. And sometimes I feel, well, there are studies basically tracing HO. Well, just only a comment to say also that there is other, because are more luminous, you can see more.
So these star-forming galaxies for H0, the distance measurements, I thank you for that. I wasn't aware of it actually.
Also
maybe I should look more into that actually, because
Yeah.
so I know of their existence, of course, but I know doing normal galaxy distance measurements is quite a dirty business because you get into like fundamental plane stuff and Tully Fisher relationship and that kind of stuff. But I also don't know about these things, so I could be wrong. Cool.
And how was the test with microquasars?
It basically seems to work.
Okay.
Actually, the bigger problem with the microquasars is that they're too variable, too fast. Actually, so you see these guys, they're varying within hours. And
So you
actually,
cannot get the information on the UV plane.
exactly. So you have to. So there's people in Perth actually looking at this, but it's actually quite difficult to handle the visibility data when you're varying so quickly, especially if you don't have SNR to pick it up. So we're thinking about these sorts of things. So actually, that is what led us to this approach that doesn't use the variability, where all you need is the candidate ratios, because microquasars tend not to be so Doppler boosted. So we often do detect candidates on it. So this is just early days, yeah. But still, when we've managed to do it, it seems pretty consistent. Yeah. Because yeah, if you use the microquasars, the other thing is how similar actually is a microquasar to a real quasar, which is by itself an interesting question. But I think for example, the actual C delta T equals 1 assumption that we make, if it turns out to be 0.97 or something on a microquasar, it's probably not going to be worse on a real quasar.
Yeah. Jet physics tend to escalate. Well,
yeah. No, I mean, it's actually a pretty interesting question in and of itself, the whole connection between microquasars and quasars. My battery stuff like that. So.
Questions? No? Extend again, yeah. You are dismissed.
Great.
So